Hello everyone, I'm Shashidhar Reddy with Canon, students of CSCI 5922, and I will guide you through our project, General CNN and Modern Few-Shot Learning. In real world use cases like medical diagnosis or tracking wildfire, we usually have extremely few images per class. Few-shot learning allows models to learn from only a few examples. We were curious to know, like, can normal CNN still perform well when data is limited? There has been a strong recent emphasis on few-shot learning, which has primarily concerned itself with Shoei architecture such as meta-learning transformers and inversion embeddings. But little has been done with traditional CNNs under few-shot settings. Our project bridges the gap. We benchmark normal CNNs such as ResNet 50, VGG16, and ConNext on modern few-shot datasets. Models and fine-tuning. Like we choose three CNN models: ResNet 50, VGG16, and Connext Waves. They were pre-trained on ImageNet. We replaced their last layers and fine-tuned with just 1, 5, 10, and 20 samples per class, hence few-shot learning. Datasets were used in this uh, project were released in the last 3 years: animal dataset from Kaggle, flower dataset from Oxford University website, and specially designed insect dataset from OpenML. The datasets included all new images to the models since there was no overlap with ImageNet. All datasets pushed the models a little bit. All images were resized to 128 by 128 pixels to have consistent input. We performed multiple few-shot experiments with an increasing number of samples. During every few-shot step, we tracked accuracy, precision, recall to estimate model performance.
Our first data set that we used was the animals data set. This was the least complex data set for our models because a lot of the classes overlapped with ImageNet. None of the images were the same as ImageNet images. However, their features were familiar to the models. This could be seen in the high performance that our models ConvNext and ResNet 50 had with their accuracy. Meanwhile, VGG16 did not perform as well. Now, our second data set was the flowers data set, and this data set was less familiar with its features to our models since it had a lot less overlap with the ImageNet data set. This showed that our ConvNext ResNet models, their accuracy did decrease. However, our VGG16 model, its accuracy did increase for this data set. And our third data set was the insects data set. This data set was the most complex for our models by far because there was very little overlap with ImageNet, and a lot of the features that these insects had was not familiar to the models at all. This showed in the performance of our different models, where ConvNext and ResNet 50, which performed the best, saw a significant decrease in their accuracy percentages, and VGG16 also decreased in accuracy. Finally, when we take a look at the cumulative results, we see down below in the plots that our top performing model by far was ConvNext, and a runner-up was ResNet 50 in blue, and the VGG16 in red did not perform well with few-shot learning on these data sets. This shows us that the ConvNext and ResNet 50 models generalize well and are able to perform few-shot learning. And we also see that as the complexity of the models increases, there is a higher and higher data dependence, meaning that more few-shot samples are required. Finally, when we view these different findings, we see that some CNN models are still quite strong with learning with few-shot learning. However, their effectiveness often depends on the complexity of the data set. So for them to venture for farther data sets and to be able to do more lesser known data sets and perform well, they often need more few-shot samples or modern few-shot learning techniques may be used. Additionally, we see that CNN architectures continue to improve as the newest model, ConvNeXt, performed much better than the older models. And modern CNNs continue to improve, though they are not well known. They're still quite effective with modern dataset challenges. Thanks for watching.